For simple cooling, the cooling coil will be placed inside our channel. The heat from our channel will be absorbed by the cooling coil to be rejected to the ambient. Similar to the simple heating, for the simple cooling, the specific humidity omega will remain constant. However, the relative humidity will be increases. If we plot the simple cooling process on our psychrometric chart, it will start from the initial state to the final state horizontally. We are going to get the specific humidity at the first state will be equal to the specific humidity at the second state. Therefore, the specific humidity will be set constant. We also notice that the relative humidity is increased while the dry bulb temperature will decrease. Similar approach will be applied to analyze simple cooling process. We are going to set inside the channel as our control volume system. The inlet section will be assigned with state 1 and state 2 will be representing the outlet section. In simple cooling, this heat is being absorbed by our cooling coil. It means that this heat is leaving our system. If we perform the mass balance for the dry air, we are going to get the mass flow rate at the inlet is equal to the mass flow rate at the outlet for the dry air. Therefore, we are going to assign it as m dot A. For the mass balance of the water or vapor, since we only have one inlet and one outlet, we are going to get m dot V1 equal to m dot V2. We know that omega is equal to m dot V divided with m dot A. Therefore, we are going to get this expression. Since the mass flow rate of the dry air at state 1 is equal with the mass flow rate for the dry air at state 2, and the specific humidity at state 1 is equal to the specific humidity at state 2, we can write the mass balance for the water or vapor in this expression. For the energy balance, the total energy coming into our system will be equal to the total energy leaving our system. From our schematic diagram, we can write our energy balance as this equation. If we rearrange this equation so that the heat transfer rate leaving our system will be the head of the equation, we are going to get heat transfer rate leaving our system is equal to the mass flow rate times with the enthalpy at the inlet minus with the enthalpy at the outlet. Please note that this portion of energy is representing the energy coming into our system, and this portion of energy is the energy that leaving our system.